Our next talk feeds into this coherent communications. It's by Dan Blumenthal. It's low energy frequency stabilized coherent WDM for data center interconnects. And Dan is a professor in the electrical computer engineering department and director of the Terabit Optical Ethernet Center. So Dan, the floor is yours.
John, can you hear me okay?
Yes.
Okay, I just need to switch over to the other laptop screen. Hold on a second. There we go.
Well, Dan's getting that up. That's his new lab in Henley Hall. It's a little empty yet, but that'll change soon.
Yes, indeed. Okay, so let's see. I'm going to share this deck of slides. Can you see that okay?
Yes, they put it in presentation mode.
Absolutely. Okay, how's that?
Perfect.
Okay, great. John, thank you for the invitation to talk today. I'd like to talk about a new technique that we use for energy efficient data centers called frequency stabilized coherent WDM for data center interconnects. This work is funded by ARPA-E under the Open 2018 program. And this is a list of all the collaborators and contributors for the work that I'll show: Microsoft, Honeywell, Northern Arizona University, Yale, NIST, CU, and then a lot of others. So we have a lot of people working on these projects and the technologies that I'll be talking about. And some of the work that I'll show is also sponsored by DARPA from the Prime AIMS program. The optical gyro program was what started our work in subhertz SBS lasers on a chip. And that work plus other atomic clock work actually stimulated the thought on how to use frequency stabilized for low energy data center interconnects. So as has been said many times in this meeting and before, there's growth in hyperscale data centers, looking at zettabytes, 21 per year in 2021, and the percentage of the number of hyperscale data centers we see increasing and climbing. Projected 2021, 53%. So somehow we're going to have to figure out how to address this type of growth. What I've illustrated here is just one data point. This is the barefoot 12.8 terabit per second switch ASIC mounted inside the Newport chassis. And you can see here a very typical architecture. This switch chip, which communicates between the top of the rack, the servers in the rack, and the outside network, or between switches and the top of rack switches, sits underneath this heat sink right here. And then we see all the pluggable optics sitting in these receptacles here. These are 32 by 400G fiber optic connections in a 1 RU. And the question is, what happens when you try to go beyond this standard architecture that data center interconnect builders have been able to rely on? And what we're seeing, and the target that we want to look at least today, is a 100 terabit per second switch ASIC. And I just wanted to give a feeling of what this actually means. So back in the 2004 to 2013 timeframe, Cisco had a system called the CRS-1. It was a 92 terabit per second system. It consisted of 72 line cards, shelves, and racks, and 8 switch fabrics that all of these racks contained optical I/O talking to the outside world, and optical I/O that talked between these line card racks and the 8 switch fabric shells themselves. This 80 rack system took a whole room, and there was a system that was actually 322 terabits per second. I don't know if one of those ever sold. But what we're talking about doing is taking this whole 80 racks and pushing all of the electronics into a single switch chip. And that just gives a feeling for the scale of the progress that's been made. But what's not going into the switch ASIC is the optical I/O. The optical I/O in and out of a system with this kind of capacity. And so we have lost the ability to track the optical I/O with what we expect will happen with the switch ASICs themselves. So I'd like to just jump to one possible outcome, which is coherent WDM. Coherent WDM is used for high capacity links. The problem is that it's very expensive and it burns really hot. So what I show here are quadrature amplitude modulated constellations that are optical, 16 QAM out to 1024 over here. And then a typical system that's used to transmit and receive a constellation. You'll take data in, you'll forward error correct it, you'll do bit to symbol mapping, pulse shaping, talk to digital to analog converters, and then like a joystick, you'll drive an optical IQ modulator that is now pushing this transmit laser amplitude and phase around this constellation in each baud time slot. And then at the receiver, we have to recover that data. We have to recover these symbols and push back out the data. That requires beating with a free running local oscillator laser. And today, the LO laser and the incoming coded data stream are pushed through an optical hybrid and detected with photodetectors. And then we go into very heavy electronic processing. We go to analog digital converters. And then we will, if you were to look inside here, you would see this spinning blurry pinwheel, which is supposed to be the QAM constellation itself. But what the digital signal processor today does is it actually calculates the frequency offset in real time and stabilizes the spinning pinwheel. So you'll get something that looks like this middle constellation here. However, you still have a phase mismatch and phase noise between the received signal and the local oscillator. And so these DSPs do real-time phase error correction, and they are able to then pull out the constellation and use IQ slicers to return the data. I've put a burner under here because these things run hot. We're looking today at somewhere around 10 watts for 400 gigabits per second of DSP power. And if you try to scale that out to 100 terabits per second, I think one can see that it doesn't scale well for inside a data center. So the approach that we take is something that we use that we call quiet light. And quiet light is if you had an optical tuning fork. So if you had a very pure oscillator that was able to transmit pretty much close to a single frequency whose phase stayed constant for a very long period of time. Today, systems that use this are like the NIST atomic clocks and the gravitational wave detector LIGO. These are tabletop systems that use very sophisticated phase stabilization and cavities to quiet these lasers down so that they are like a tuning fork, and they can achieve stabilization that's on the order of some of the lowest line with atom transitions that people use today. So we're talking about quiet light, which is spectrally pure, frequency stable, and also has amplitude stability too. And so the question is, can you use quiet light to offset the energy consumption of a coherent link and then put that inside a data center? And so this is indeed what we're doing in the FRESCO project. This is a vision figure that shows the following. It's the ASICS switch, which is running at 100 terabits per second, sitting next to a co-located, and Catherine talked about this, co-located photonic chip. The photonic chip has a quantum dot tunable laser that serves as a semi-quiet light that then pumps a stimulated Brillouin scattering. It's a certain kind of laser that I'll show you, SBS laser that then quiets the light up even more by a factor of 100 to 1,000 in terms of phase noise. And then we bolt that light to a frequency stabilized resonator that really quiets the light down. So now we have a really pure, quiet optical tone on chip that we then replicate across the whole WDM spectrum. And this is done by pumping a comb frequency generator. And now we have a really quiet comb. The comb is used for both transmission and for the local oscillators. And we then push these through more traditional silicon photonics QAM transmit and QAM receive chipset, although we are pushing the boundaries there also in FRESCO in terms of baud rate and constellation space. We're trying to go out to 72 gigabauds per second and 256 or 512 QAM, which is way beyond the state of the art that people can do today. So the point is that we're doing a co-located architecture using quiet light. And what I'll show you is that this architecture is DSP-free. It doesn't require high-speed digital logic inside the tracking system itself. There are no high bandwidth optical phase lock loops or electronic phase lock loops. These are the analog alternatives to DSPs. There's no COSTAS loops, no out-of-band carriers. So by putting our energy into stabilizing and quieting the light, we get rid of a lot of the high bandwidth or power consuming digital electronics that are needed for one of the more important functions, which is optical carrier and phase recovery. And so I'd like to just draw a quick analogy of what we're trying to do here. You can imagine having two very large ships. They don't have to be aircraft carriers. They could be cruise ships. For example, sitting in our Santa Barbara Harbor here. And these ships are the very large mass, so wind and wave action will not perturb their position, and they'll dampen out any kind of vibrational noise. And if you look closer, you'll see that there's two sailboats that one each attached to each of these large masses. Let's imagine that the sails are down. And if you look even closer, you'll see there's two people, one trying to thread the needle from one sailboat to the other. And I think we can imagine that if we took away these large ships, that these two people would be running around a lot, expending a lot of energy if they could even thread the needle. But anchoring them to some kind of a mass will make it possible to thread the needle and certainly doable at lower energy. So we can now imagine having what we call a thermal and optical mast called a microcavity. It's a reference cavity that we're going to tether a tunable laser to. And the tunable lasers are the transmit laser and the local oscillator. And those are going to be beat together, signal and local oscillator into a photodetector, and threading the needle is going to be like putting the intermediate frequency through a channel filter. And if we can get an energy win with the stabilization over what you would need to do otherwise, then this becomes an attractive, scalable approach. So this is what we've built to date. This was presented at OFC 2020, Grant Brodnick and co-authors. And what you see here is a laser PIC that's pumping a silicon nitride cavity here. This is a resonant ring cavity that we actually create the quiet light using Brilliant phonons, Brilliant gratings. We take out the tone that's generated by this laser and we create a sideband with an acousto-optic modulator, and that sideband is tethered to our billion Q cavity. So we have a NIST cavity, which is a 1 billion Q, very stable cavity, and we use circuits called PDH lock electronics, and we basically create a very stable signal for the transmit and for the local oscillator, and I'll show you the results of what this looks like. It's just important to say that these PDH lock electronics, because of the stability of our signal, they're running at 100 kilohertz, couple hundred kilohertz bandwidth. The signals are so quiet and stable that these lock electronics each can be put on a CMOS chip for 1 milliwatt power. So just to give a sense of what we're talking about here, we can transmit WDM terabit channels, say 10 terabits, by using several milliwatts of CMOS electronics to do the phase and frequency stabilization and recovery. So it's quite a different domain than what people do today. Here are some results, and I also put in here some very, very recent results that we have to show also. So what you see here on the left-hand side is a Morton Photonics tunable laser, just in this particular experiment, that pumps the silicon nitride cavity and creates the quiet light. The quiet light is anchored to our NIST microcavity here. It's about 1 centimeter long, which acts as the large shift. And we're not with the same performance, but with similar performance. We're taking a LIGO type system and putting it at the chip scale. And what you can see happening here is if you look at this graph here, this is the frequency noise of the system. This blue curve here, the dark blue curve, is our free running Brilliant laser. Now, it itself is extremely quiet. The Brilliant laser itself has under 1 hertz fundamental line width, which is shown out here at the high frequencies. However, all the close to carrier noise is what we call the shoulders and the integral line width. But when we attach it to the cavity, you can see that we bring this noise down by many orders, 5 orders of magnitude. As a matter of fact, this shaded region right here, the laser is so quiet that our measurement system is too noisy. So I'll show you how we get around that. We also measure something called the Allen deviation, which shows the stability. And just using this chip scale system, we're able to get better than 10 to the minus 13th fractional frequency stability over 100 milliseconds. And that's pretty amazing. That's getting close to atomic clock performance with chips. And this is what we use for our system. I just wanted to show you a very recent result that's been posted to arXiv. We are working with the ARPA-E FRESCO project and also the A5 project for atomic clocks, putting these frequency cavities on chips with waveguides. And so what I wanted to show here in the lower left right-hand corner is that we've set a world record with a ring resonator that has 422 million Q on a chip. And that's under 1 megahertz line width. As a matter of fact, the intrinsic line width is 400 kilohertz. And so we're looking at the capability of now putting these kinds of reference cavities actually on the waveguide chip with the other photonics. And we measure something called the absorption limited Q for this cavity is 3.4 billion. So we think there's a lot of room to improve here, and we are really excited about the integration of everything that you see here. So now to measure the line width of these lasers, our normal measurement system can't keep up with the low frequencies. It's too noisy. So we built 2 of these lasers, one each on separate optical tables. So they are now running independently, and we now beat them together and we thread them through a 160 megahertz filter. And we now use something called an electronic frequency discriminator. So these are 2 completely separate lasers that don't have anything to do with each other. And when we beat them together, we measure a 30 hertz integral line width. And I mean, this is amazing for 2 separate lasers that are at the chip scale. It's an unparalleled frequency stability and low frequency noise. And so this is what we're able to now use for coherent communications. So you can see here even more detail of the frequency noise that we can show and the line widths that we look at. So we spend a lot of time and pay a lot of attention to the noise sources here and bringing them down. And now building a coherent link. So what we're looking at here is a 16 QAM 50 gigabaud system that's being transmitted on one of those 2 lasers that I showed you, the stabilized lasers. And now they're being sent to the other table, which has a hybrid and a local oscillator that's sitting there. And it's also one of these stabilized lasers. And then what we do is we use something called an OFS PLL, an optical frequency stabilized PLL, to now align the sideband modulated from the local oscillator with incoming signal, and they frequency and phase lock. And we only need a couple of 100 kilohertz to do this. So again, this is an astoundingly low energy needed to transmit terabits of data on a channel. And what we did is we built 2 comparisons. One is we did self-homodyne, where you take the transmit laser carrier itself and you mix it at the receiver. So you can't do better than this. And we recover the constellation. And that's my doorbell with a tail. Sorry about that. We compare that to, hold on a second, guys. Okay, sorry about that. So we compare that to running a DSP. So this is what you would do in these links that I showed before with the DSP that does frequency tracking. You can see the blurry, pinwheel being stabilized with frequency, and then the phase lock is turned on. So we get the constellation back. So we are now measuring the performance of a homodyne, which is the best you can do, with the DSP. Then we turn off the DSP completely, and then we run our OFS PLL and turn on that very low bandwidth lock loop, which recovers the data. And then we measure.
You can wrap up, Dan. We're running pretty late.
Okay, the error vector magnitude here is shown. This is the last slide. We measure the error vector magnitude, and we compare the homodyne DSP and our FRESCO technique. And you can see that as we go from baud rate 32, 40, and 50 gigabaud, that we're within a percent or two of the homodyne and the DSP. So what we've done is we've shown that this system can now perform as well as a DSP system, but with orders of magnitude less power. Thank you.
Great, thanks, Dan. We're about 10 minutes late now, so we might move on, and but we'll hopefully get questions during the panel session. So thank you very much, Dan. That was really impressive results.